So these are the topics of today. We'll discuss about two topics. First, we'll discuss about thin-walled pressure vessel, which gonna utilize the 3D Moore circle that we have learned in previous class, and then we'll discuss about Moore circle for plane strain problem because we already covered plane stress problem. So let's begin from the first topic, thin-walled pressure vessel. So when you maybe travel along the highway, or when you go to some like a port, you may have seen these kind of pressure vessels. Some pressure vessel has completely spherical shape, and the other types of pressure vessel looks like a cylindrical shape. And of course, in terms of symmetry and the safety, spherical vessel is better than cylindrical vessel. Just simply by intuition. Of course, I'm gonna provide you more quantitative proof about it. However, even though the spherical vessel is more symmetric and more safe in terms of the efficiency of using the space, this sphere has much more empty space, right? These are the place where you can fill the gas, and out of this array of the spherical vessel, you cannot utilize this void area, void volume, right? However, if you consider cylindrical vessel, then you can have like a much better efficiency in utilizing the space, and there is pros and cons. So that's why in some places where you have a huge space, you're gonna see like a spherical vessel more, and in some place with like a higher expense in land and more expensive area, then you're gonna see the cylindrical vessels. Okay, so we'll today analyze two kind of vessel, so cylindrical vessel and spherical vessel, and we gonna focus on the condition on thin-walled pressure vessel. Okay, so please note that the discussion we're gonna have today only applies for thin-walled pressure vessel. If you consider thick enough vessel, you cannot apply the knowledge we learned today. So let's discuss about the cylindrical type first. So out of the cylindrical type of vessel, let's try to make a cut, and let's take this infinitesimal volume. So let's take this infinitesimal volume, then you can think about the stress along the radial direction, and you can think about shear stress on top of the surface. So at the outer surface of this pressure vessel, you can think that there is no stress acting on, like no normal force, no shear force. In that case, we can say for sure that sigma r will be 0 and tau will be 0. Inside this vessel, you're gonna have a gas with pressure larger than the atmospheric pressure, and of course you might think that there would be effect of pressure, so that you might have sigma I component that is non-zero for this vessel. However, for only for thin-walled vessel, where T is much smaller than R, then you can people already prove that sigma R is almost 0 inside the vessel. So this condition only holds for when T is much
larger than
the radius of the vessel. And regarding the general thick walled vessel, we're gonna discuss about it in next semester, which is the solid mechanics second class. Okay, so given this condition, like we don't have any radial component of normal stress and shear component, including the radial component, then we can convert this problem into the plane stress problem. So suppose that the direction along this circumference of a circle is direction 1, and direction along the long axis as direction 2. We can define sigma 1 and sigma 2 as two normal stress when you take this as coordinate system. If you take your coordinate system in this way, suppose that this is side view of the cylinder, and you are taking first axis and second axis in this way. Due to the symmetry, you don't expect any shearing stress occurring for this pressure vessel if you take your coordinate system as here and there. Okay, so this is the simple stress state you can imagine when you take axis in this way along the hoop and along the longitudinal directions. Okay, so this is a typical plane stress problem with sigma g, which is sigma r in this problem is 0, and all shear stress component is 0. Okay, so now given this coordinate system, let's try to get the stress component sigma 1 and sigma 2 normal stress component. So to obtain the normal stress component 1, the normal stress along that direction, let's try to get this red area. This is the front view, and if you take the cross section view, this is a half circle out of this thin-walled vessel. So if you think about the free body diagram, the within this area there will be some gas, pressurized gas in the other side of this red area. So you're gonna have some sort of pressure to upward to this our volume of interest, and due to this pressure, and there is like a area, so you have to have like a P times delta A. So you have this infinitesimal thickness dl, you have like suppose that this is 2r, radius is r, and this is diameter, this is 2r. Then you can define the pressure multiplied by area and its upward force. To balance this upward force, you need a downward force, which is sigma 1 multiplied by dA1. Let's call this area as dA1 and A1. Then after combining these two equations, you can write down mechanical equilibrium equation along this vertical direction. So you have PdA. This dA is 2r. This is the 2r multiplied by the thickness dl. And regarding the dA1, you have thickness t. The thickness of this guy, thickness is t, and you have dl. So this gives this dA1 area, and you have two of this area where sigma 1 is acting on, so you have vector of 2. So after plugging these expressions and try to massage the equation to obtain sigma 1, what you're gonna end up is, after massaging this way and cancelling out dl here and move this t and 2 term to that term, then you're gonna end up having sigma 1 equals to be P times radius of the vessel divided by thickness of the vessel. Okay, it is called hoop stress. And we can think about the stress along the other direction, which is longitudinal direction. Out of this front view, we just obtained the sigma 1, and it's time to obtain sigma 2 along the longitudinal axis. So to obtain that, let's try to get some volume of interest, and here the analysis goes in quite similar manner. We have P times area dA prime here, and we have sigma 2 multiplied by this shell area colored in red. Okay, and they must be balanced out in mechanical equilibrium condition. And this dA1 A prime area is pi r square. This is simply the area of the cross-sectional area of the gas tank, and dA2 is 2 pi r, which is the circumference of this cross-section area, and the multiplied by the thickness of the pressure vessel. After plugging these expressions here and there, you can you end up having the equation for sigma 2, and sigma 2 turns out to be PR over 2T. So you can find that the pressure along the longitudinal direction is half of the sigma 1. So based on this sigma 1 value PR over T and sigma 2 value PR over 2T, you can write down 2D in-plane Mohr circle. So as I told you, when you take your axis 1 and axis 2 here, this is 2 is the longitudinal direction. and then you don't have any shear stress, so it's quite easy to complete the Mohr circle. Here you have two principal stress, sigma 1, oh no, it must be PR over T, and sigma 2, this is hoop stress, this is longitudinal stress. Then after completing this Mohr circle, and you can find that the radius of this Mohr circle is given as half of sigma 1 minus sigma 2. This is sigma 1 minus sigma 2, and if you take half of that, it gives you PR over 4T. So when you design a pressure vessel made out of ductile metal, and if you use the maximum stress as PR over 4T, you're gonna have wrong answer and wrong design for pressure vessel. The reason is we didn't consider 3D Mohr circle. If we complete 3D Mohr circle, because along the radial direction or along the G direction, we have another principal stress which is 0. Okay, after considering this principal stress, you have 1, 2, 3 principal stress, and after completing I missed it here. After completing these 3 circles, what you're gonna end up is the maximum stress turns out to be sigma 1 over 2, because this the length here is sigma 1, and if you divide this by 2, and it gives you the actual value for maximum shear stress in considering full 3-dimensional rotation. And you found that the estimation for maximum shear stress turns out to be twice larger than the maximum shear stress expression you found from 2D analysis. Okay, so in designing the cylindrical shape of pressure vessel, you have to consider that the allowable stress is larger than the maximum stress, which is given as PR over 2T. Okay, so please be careful about it. And then if somebody asks you where is the failure plane, what you have to do is following. So so as I told you, this plane, the largest plane, somehow passes through sigma 1 and sigma r. Okay, so out of this pressure vessel, okay, so let me give you some more graphical sense. Out of this pressure vessel, this is direction 1, this is direction 2, and you have out of this plane direction. So and the third direction is radial direction, and first direction is here. So this purple circle, the largest circle, is rotation about axis 2. This axis. Okay, rotation about that axis. So if you take out some volume here, you're gonna have this kind of volume, and you have direction 1 and direction 2, and you are rotating about 2. And if you rotate with respect to 2 by 90 degree, 2 theta is 90 degree, you're gonna have maximum shearing stress. And if you consider rotation about 2, you can see that because 2 theta is 90 degree, if you have 45 degree, and this is the radial direction, then you're gonna have a maximum shearing stress occurring along that direction. Okay, so regarding the failure, if you saw some failure of cylindrical pressure vessel, it is likely to occur along this 45 degree angle, and it may occur along that plane, right? So you can predict not only the the failure itself, also the failure mode, okay, and failure plane too, by considering 3 Mohr circle problems. Okay, so this is about the cylindrical shape pressure vessel problem. Now let's move on to spherical shape pressure vessel. So in spherical vessel, for any rotation, you can take a axis in any 2 orthogonal directions, and it will be pure in plane and symmetric mode, and there will be no shear stress, because due to the symmetry, you cannot distinguish any directions. Okay, so the problem is relatively simple. So you're gonna have sigma 1, sigma 2 equal to each other, and tau will be 0. Okay. Okay, so in that case, let's try to get the value for sigma 1 and sigma 2, which is basically same. Then let's try to get, the half of the sphere, and within this the black dotted center, you have pressure of gas multiplied by the circle area, which must be pi r square. And to balance this out, you have sigma 2, and sigma 2 multiplied by dA. dA must be circumference multiplied by thickness t. Yeah, thickness t is here. Okay, then after writing down the mechanical equilibrium equation, you end up having this expression, and sigma 2 turns out to be PR over 2t. Okay, so if you compare this, this is the same as the longitudinal stress, which is PR over 2t, and it's half of the hoop stress. So hoop stress is given as PR over t, and this is somewhat expected because when you have like a more symmetrical structure, it will have like a smaller stress concentration and smaller value of stress to hold the same pressure. So now after obtaining the normal stress value, which is same sigma 1 and sigma 2 equals to be PR over 2t, if you complete the 2D Moore circle, it is simply just a point, like a PR over 2t. So if you consider 2D Moore circle and consider the maximum in-plane shear stress, it's 0. Okay. However, to do like a real design of the pressure vessel, you have to consider 3D Moore circle, and the other principal stress is given as 0. And after completing this circle, you're gonna find that the maximum shearing stress will be simply the value of this guy divided by 2, which is the radius of this, and it's given as PR over 4t. Okay, so if you consider the maximum shearing stress for spherical shape, it's PR over 4t. If you consider maximum shearing stress for cylindrical shape, it's given as PR over 2t. So you found that the maximum shearing stress for spherical shape and for same pressure and same radius and same thickness, the maximum shearing stress for sphere is the a factor of like a 1 over 2 compared to the cylindrical vessel. Okay, so this is somewhat expected, and that's why I told you that the spherical vessel, given similar geometrical value, same pressure, same radius, and same thickness, spherical vessel is more safe. Okay, but however, even though the spherical vessel is safer in terms of the efficiency in space usage, the cylindrical vessel is better. So for relatively low pressure and like a cheaper gas, you'd better use cylindrical vessel. For very expensive gas, or when you have like large land and space, you can use spherical vessel to your choice. Okay, and with that, we considered one case of problem where we can utilize the in-plane plane stress problem and 3D Moore circle like 100%. Okay, so hopefully this gives you some idea on how to design the pressure vessels you should have seen in your life in several times. Okay, so with that, let me finish my discussion on the first topic of today.